Find the design compressive strength in the column in pounds. In this problem, two C12 by 25 members are positioned back to back with a separation of 10 inches. The effective length of the column in both the x and y directions equals 20 feet, and the Young's modulus and yield stress of the steel are provided. The design strength of a column equals BC times FCR times AG, where BC equals the resistance factor for a column, FCR is the critical stress, and AG represents the gross area of the column. From the problem statement, we know BC equals 0.85. The gross area can be determined by looking up the area of a 12 by 25 channel member and multiplying that area by 2 members, which equals 14.68 inches squared. The critical stress in the column, FCR, is computed using one of two equations, which depends on the slenderness ratio and the value 4.71 times root E over Fy. We'll first determine these two values so we know how to compute the critical stress. We'll plug in Young's modulus and the yield stress into the right-hand side and find the right-hand side equals 113.43. Next, we'll solve for the slenderness ratio, KL over R. The most conservative slenderness ratio is the largest slenderness ratio between the x and y axes. From the problem statement, the effective length about both axes equals 240 inches. The radius of gyration, r, equals the square root of the area moment of inertia divided by the gross area of the column. We've already computed the gross area as 14.68 inches squared. The area moment of inertia equals the sum of the centroidal area moment of inertia plus the area times the distance from the centroidal axes for each channel member. Since both channel members are symmetric about both axes, we can simplify the equations. Next, we'll look up the centroidal area moment of inertia for both the x and y axes for a C12 by 25 channel member. From earlier, we already know the area of a single member. Next, we'll focus in on one of the two steel members. Here we notice the centroid of the member lies on the x-axis. Therefore, the distance dx equals 0. To find dy, we'll add 5 inches to the length y bar, which for a C12 by 25 member, y bar equals 0.674 inches, which makes dy equal to 5.674 inches. After plugging in the known variables, the area moment of inertia equals 288 inches to the 4th power and 482 inches to the 4th power for Ix and Iy, respectively. Next, we'll solve for the radii of gyration about both axes, where Rx equals 4.429 inches and Ry equals 5.730 inches. Now we can solve for the slenderness ratio by dividing the effective length by the radii of gyration. The slenderness ratio equals 54.19. Since we know the left-hand side of the equation is less than the right-hand side of the equation, we'll use the first equation to solve for the critical stress in the column, which is the last unknown variable we need to solve for the design strength of the column. From the problem statement, we know the yield stress of the steel, Fy. The buckling stress, Fe, equals pi squared times the Young's modulus divided by the slenderness ratio squared. We know the Young's modulus, E, and we already computed the slenderness ratio, KL over R. This makes the buckling stress equal to 97,467 pounds per square inch. And subsequently, we compute the critical stress to equal 40,339 pounds per square inch. And finally, the design compressive strength of the column equals 5.03 times 10 to the fifth pounds. When reviewing the possible solutions, the answer is C.